Modern civilization runs on stored energy. Phones, laptops, electric vehicles, renewable power grids, and even emergency medical devices all depend on one quiet chemical miracle: the battery. Energy chemistry explains how chemical reactions are designed not just to release energy, but to store it safely, transport it, and release it on demand, anywhere in the world. This is the Learning Studio, where chemistry is explained as the engine behind modern infrastructure. And after understanding how atmospheric chemistry and fossil fuels reshape the planet's climate, the next logical step is to understand how chemistry is now being used to power the world without burning it. Most people think batteries are just containers of electricity, but in reality, they are controlled chemical systems. For example, when your phone battery charges and discharges, no electricity is being stored like water in a tank. Instead, chemical reactions are reversibly moving electrons between materials, converting chemical energy into electrical energy and back again. At the molecular level, batteries work through redox reactions. One material gives up electrons while another accepts them. These reactions are kept physically separated inside the battery, so electrons are forced to travel through an external circuit, creating usable electric current. The voltage, capacity, and lifespan of a battery all depend on the chemical properties of the materials involved and how easily ions and electrons can move. The foundations of battery chemistry began with Alessandro Volta, who demonstrated that chemical reactions could generate steady electrical current. Modern battery technology, however, was transformed by scientists like John B. Goodenough, whose work on lithium-based materials made high-energy, rechargeable batteries possible. His discoveries turned batteries from bulky power sources into compact, high-density energy systems. Lithium-ion batteries became revolutionary because lithium atoms are small, lightweight, and highly reactive. This allows ions to move easily between electrodes while electrons flow through circuits, delivering large amounts of energy relative to weight. Carefully engineered electrode materials ensure that this process remains reversible, stable, and safe over thousands of charge cycles. Energy chemistry also determines the limits of battery performance. Heat generation, degradation, charging speed, and safety all depend on chemical stability and reaction control. Improving batteries is not just an engineering challenge, it is a chemical one, requiring better materials, improved electrolytes, and precise control of interfacial reactions. The impact of battery chemistry extends far beyond personal electronics. Batteries enable renewable energy storage, allowing solar and wind power to be used when the sun isn't shining or the wind isn't blowing. They power electric vehicles, reduce dependence on fossil fuels, and reshape global energy systems. In this way, energy chemistry becomes a central tool in addressing climate change. And once we understand how chemistry stores and delivers energy through batteries, the next question naturally follows. If chemical energy can be converted into electricity, then how can chemistry produce electricity directly from fuels without combustion? That question takes us directly into the next episode, where we explore fuel cells and hydrogen, chemistry's role in the future of clean energy.